Hi, we are Berta and Carlota, and we will explain the F-test for two variances. An F-test is used to evaluate which method is more precise. It consists of comparing the experimental and theoretical value of F. As we can see on the screen, the experimental F is calculated by dividing the variances of the two methods, whereas the theoretical F will be estimated by taking into account the value of the degrees of freedom of each method. On your right, there is a plot for an F distribution. It's important to point out that the area under the curve represented corresponds to the level of significance, which we'll talk about later.
There are three types of F-tests, each one of them with its statistical hypothesis. For starters, we have the two-tailed test, which divides the area in two parts, each one worth half the alpha value. The null hypothesis is the same for the three types, and it states that the two variances are equal. For the two-tailed test, the alternative hypothesis says the variances are different. Regarding the one-tailed test, the area underneath the curve corresponds to alpha. In these cases, the alternative hypothesis states one of the two variances is greater than the other. In every case, when the null hypothesis is rejected, the alternative hypothesis is considered correct. Depending on the question that wants to be answered, we have to choose which one of these F-tests fits the best.
In order to find the theoretical F, we will have to look at the tables of the F distribution for the value of our level of significance. The level of significance indicates the probability of rejecting the null hypothesis. Besides, there is one table for each level of significance, so we will have to choose the specific table for the alpha that we are working with. What's also relevant is the fact that in case we are doing a two-tailed test, we have to look at the table for half the value of the level of significance wanted, because the tables refer to a one-tailed test.
Now we'll see how to read the tables. First, we have the columns that represent the degrees of freedom in the numerator. In a two-tailed and right-tailed test, the numerator corresponds to the highest variance, whereas in a left-tailed test, the numerator is the lowest variance. Next, we have the rows. They correspond to the denominator's degrees of freedom. In this case, for a two- and right-tailed test, the lowest variance is the denominator, and in a left-tailed test, the highest variance is the one corresponding to the denominator.
In the table, we can find the F values. Each one of these is associated with a specific combination of degrees of freedom.
To finish off, we need to calculate the experimental F value. We've seen that it is obtained with the formula on the screen, but we have to find first the variance for each sample. The variance is calculated with a simple formula on the left. Once we've found both F values, we have to compare them to conclude the test. Only if the experimental value is greater than the theoretical value, the null hypothesis can be rejected. Let's look now into an example. We have 10 different temperature measurements for 2 different years that correspond to the A and B samples. The degrees of freedom are 9 for both of the samples. Then, applying the variance formula, we can find the value for each of them. Next, we proceed to calculate the experimental value of F, in this case being 1.17. We want to determine whether the variances are equal or not, so we'll do a two-tailed test. We want a 95% probability, so we use alpha 0.05, but since we're doing a two-tailed test, we look at a table for alpha 0.025. There we find that the theoretical value of F is 4.03. So, the experimental F is not greater than the theoretical, so we cannot reject the null hypothesis.